I will start to share my screen now, and I think we can start right away with the presentation. Okay, I just want to make sure that if everyone should be seeing my screen right now. I would also like to thank the Toronto sector of IEEE and Mostafa and Monsoon as well for the introduction and the opportunity to share our knowledge and expertise in this chapter. So yeah, today this discussion will be focusing on electrical safety and ground fault monitoring for electrical vehicles and charging station. For those of you that, if some of you are not aware or does not know Bender in particular, just a quick introduction. Bender is, Bender Canada, part of the Bender Group, is a German manufacturer of ground fault electrical safety products for more than 80 years, starting with our founder Walter's Bender vision 80 years ago of providing comprehensive protection against the dangers of electrical current. A problem that was occurring in the German mines in that period, that he came up with the first patented insulation monitoring device shown here in this picture. And that idea has driven us to this day. Still a family-owned company, now in the third generation, still in the same old town of Grunberg, Germany, of our founder, with more than 900 plus employees in more than 70 countries. We employ more than 50% of our resources in research and development, in producing more accurate, more advanced technologies for electrical safety in general in all sectors of activity. Of course, we also have a lot of information. If you'd like to know, whatever, we're doing webinars more like this, and Lounge and Learns on our website. You can connect with us on LinkedIn, and if you'd like to learn more about also with our Monitor magazine, feel free to reach out to us. We'll be more than happy to help in all regions of the world. Today we'll focus particularly on the protection mechanism for ground fault detection inside electric vehicles, the insulation monitoring products that are being used available for EVs. Then we'll focus on the charging type, the charging aspect for, of course, for electric vehicles, the different type of charging in North America, looking at the particular electrical standards being enforced. In particular for level 2 and for level 3, what is the technology and the products being used for those types of charging station. Then we'll conclude, and of course we'll have time to answer many of your questions. So the idea for insulation monitoring, in particular for what is being found on electrical vehicles, is the ideas of how we can ensure electrical safety under extreme conditions that any commercial vehicle or even high performance vehicle like a Formula 1 could find into. High temperatures, low, snow, rain, etc. All those conditions that, especially for an electric vehicle, would be considered extreme for in those circumstances. It's in terms of the products that Bender, or the idea or the vision for sensors inside vehicles, is that we have 3 types of solutions. The first one would be in a case where we want to integrate, where we can integrate our technology inside, let's say, a BMS, for example, that is highlighted here on the top of the solution, where it's more of a license for OEM, established car makers. That could be a solution. Then we also have a standalone insulation monitoring that will be like a standalone black enclosure that will be very useful for new car makers, startups. And finally, specialty type of products where there are extreme conditions, like for the Formula 1 or Formula Electric, or large buses or large trucks that could have more. That could introduce more of that would more of an expertise or special functions built into the product. All of that is part of our Bender portfolio, or the vision that Bender wants to introduce with looking and providing a solution in all types of application for EV. Now, you might be wondering, what do we want to detect in terms of insulation monitoring? The answer to that is there are imperfectness in all electrical distributions, meaning that you could have, loss of insulation. Let's say as you can see, that the conductors are now stripped, are stripped away and now can be are connected or leaking to ground. It could be just a straight disconnection or a cut cable. Accidents are also another reason that you would find insulation faults. Most of the electrical faults found in all distribution, not just EV, but in all distribution, are caused by phase to ground faults. In that essence, it's what we refer to as insulation fault. And that's why there's a very strong need for an accurate and a precise monitoring mechanism for insulation monitoring. This is just another few of those examples of those instances where we want to be able to detect those kind of incidents before we reach a critical point of risk for personal protection or for equipment or fires, etc. So in other words, things will happen. So it's up to us, as in case of Bender as a supplier, and in the case also for manufacturers, car makers, to provide a means to measure, prevent, and protect against those insulation faults. So the main idea behind insulation monitoring, if you're looking at the technology point of view, would be very similar if you're familiar with Megger. We all do in a mini electrical distribution, we do a Megger test where we put the system offline, we connect the portable Megger that is injecting a high voltage in the system, and the result is an insulation resistance calculation being done, and in return for one value, and that's it. In the case of the insulation monitoring from Bender and other devices, would be it's online. So the system is still online. Then we inject the insulation monitor would inject a signal, superimposing on the existing voltage, and then doing the same calculation of insulation resistance. So the main idea is that, of course, on a DC system in EV, we're measuring between the positive and the negative leg against the ground, or in this case, the chassis of the vehicle. So the higher the leakage, the higher the insulation resistance in the megaohms, the better that electrical system is isolated and healthy from the ground. When the value drops down, then the insulation, you could either have an insulation fault, or in the worst case, down to zero, could be then a bolted phase to ground fault. So the point is looking over time, the insulation resistance. And as in every distribution, we all know that components, motors, cables degrade over time. They will not remain completely isolated, and they will degrade over time. So the insulation resistance will drop over time. And the main idea, the vision from Bender, is to provide an alarm advance in time before we reach a certain value of an insulation resistance that would be critical, that would be a risk for personal, plant, or fire protection. So again, we always provide, and that the example on the right are the more of the industrial type of product, but the principle also applies for EV, where there are two levels, set points being provided, one for warning, that will then allow to give a signal or indication for the driver, for the EV, that they need to bring their car in for service and repair for their vehicle. So advanced information allows to ensures that we're not reaching the critical levels that would be a risk for safety. So just as a quick overview of what would be inside an EV, a battery electric vehicle, you would have, of course, the vehicle connectors for charging, AC onboard charger, a DC contactor for the fast DC charging, the battery itself, and then the inverters for the AC mode, the main propulsion motor, the air conditioning and other loads as well, and other DC-DC conversion for low voltage as well. So the insulation monitor, we call here in this graph IMI, and I'll explain that later on. It's per the standards. It's being connected directly into the positive and negative, the red and blue lines, and it's also referenced to ground. The ground in this case is the chassis of the electric vehicle. That is essentially the equipotential bonding of the wall electrical systems. And you will also notice that there are also galvanic separation in certain equipment, in particular the AC onboard charger and the low voltage, the converter. In the case of the IMI, and I'll talk about in a moment about the technology, the principle of that signal being superimposed, that signal cannot pass through the other side of a galvanic separation. So it always will be limited to that network, in this particular case, the DC of the battery, but also in the case of the inverter to the motor, there's no galvanic separation. So it's also monitoring the AC side of that system as well. But it is not going to monitor the LV, the low voltage of that system, because of that galvanic separation. So just a quick overview of what would be the level of what the IMI will see overall inside the electric vehicle. So here, speaking of which, the principle being used by Bender for electric vehicles, we call it the active measuring phase correlated pulse, PCP. The main idea is of an injection of the pulse DC signals, as shown on the bottom right of here. That injection will allow to I'm sorry. So this signal, this measuring signal will allow to pass through every single component, AC and DC, of that system. That signal through that RF resistance of the insulation resistance of the system here shown on the right, that signal will generate a current. That current will be measured by the Bender unit inside the isometer, the insulation monitoring device, compared to a reference value of the resistance, and then that will be then returning a value of that resistance, or the overall insulation resistance of the wall system. The main things about this adaptive measuring principle is in fact it is adaptive. It is an active, so it is going to adjust its frequency and its amplitude depending on what is being found on the system. Monsoon asked a very good question about switching frequency with onboard converters inside the vehicles. We know that we don't have the time today to talk in detail about this, but just as a quick summary, the adaptive measuring principle allows to adapt in situation with different level of frequencies. So it is really robust against noise and voltage drops. So it's really, let's say, if you're comparing to, it's a common problem being found in the typical bridge IMD principle that Bender does not use, that are commonly result in low level of inaccuracy in general. Bender is avoiding this with its active measuring principle. So with its accurate measuring principle, it's also capable of detecting symmetrical faults. And what I mean by symmetrical faults, it's a fault that is occurring simultaneously on the positive and negative leg of a system, or L1, L2 in this case. So that's what we mean a symmetrical fault. And so there's no high voltage needed. It can start measuring already at 0 volts, so offline monitoring is also possible. One of the main small disadvantage, and it's really about high leakage capacitance. We're in the process of fixing that. I'll talk about the products in a moment. But in typically in an electric vehicle, we're not going to be finding high level of leakage capacitance anyway. But that's one of the limitations with this technology. So speaking of different products available for ground fault detection and safety inside an EV, there are two main products, and the third one is being in development. The first one is the ISO 165, which is come with in an automotive grade enclosure and connectors. It's using our own Bender CAN high-speed CAN interface. Up to 600, it can be used up to 600 volts of a distribution, and it has up to 1 to 3 microfarad of a limited range in terms of leakage capacitance. Leakage capacitance will be in all those products in terms of IMI and IMD will be the main thing that we'll be looking into when we're selecting or proposing a product. We'll be looking at voltage and the leakage capacitance. The second product, the IR155, would be the PCB style of a product that will, instead of doing an enclosure, you can now integrate it into a BMS or a different component inside an EV. It has a bigger range for voltage, the same range for leakage capacitance. For information, we are designing a new product that will be a successor for the IR155, which came with only the PWM output along with a standard alarm output. Now with that successor, we'll also be introducing capability with ACE J1939 CAN interface, along with another variant for PWM. We will also be introducing a higher level tolerance for leakage capacitance up to 10 microfarad. So that will be addressing a larger application like a truck or a battery electric bus. And that the production its expected release will be sometime in 2021, so next year. I just want a quick reference about the different products for in the IMD. In this case, the ISO 165. There are different two variants for the interface for the speed, 250 or 500 kilobits. And that it also has onboard internal decoupling relays. That means that you can keep the IMI isolated from the main system. That will be very important for charging, for example. And it's also capable of measuring the voltage during that case, where we can measure the voltage, and when we're ready to start up, then it will measure the voltage, everything is fine. Then it closes the internal coupling switches to start the measurement of the insulation. In the case of the IR155, that one doesn't come with internal coupling relays, but it is, as I mentioned, a higher level of compatibility in terms of voltage. So it's being used really more in the hybrid trucks and the higher voltage systems in general, compared to the other one, which is more for commercial vehicles. But again, the main advantage of this one is this can be easily mounted inside a control box or BMS or whatever, that you will have space for that very small and compact design PCB. As you can see, these are just dimensions of those solutions from Bender for insulation monitoring. So very compact, so it can be very easily integrated into a car maker design for the best in class for insulation monitoring. So just as a summary here, just before we can move on with the charging stations. Bender has been chosen by many car makers across the world because our 80 years of experience in the mines and all the different in ships and offshore application, which also all of them introduce switching frequencies, switching power supplies, AC inverters, rectifiers, a mix of AC and DC. All those conditions helped up to create the best technology with an active measuring principle for reliable monitoring. So that also works very well with this automotive environment, because Of course, the variation of voltage is the reality for EV, the harsh environments on temperature, etc. That's another thing that Bender is able to withstand in terms of temperature changes and so forth. In the ability to detect asymmetrical and symmetrical faults is also a big plus that allows for detection every type of situation that can occur inside an EV. It's also having advanced integrated functionality, such as ground checks into its own connection, making sure that they are actually connected to the chassis ground of the vehicle. These are some of the, and stuff like the self-test is a few of those functions that really allow customers to trust Bender and implementing Bender and giving them a peace of mind that they can rely on that product to make sure that their EV is safe and safe to operate. And of course, there's a lot of business models. We're very flexible in general with different products that I mentioned up to now. So we'll now switch into the charging station now, which now brings other topics. Because inside an EV, there's not much in terms of standards being enforced overall. That could change, of course, but for EVSCs or electrical vehicle supply equipment, there are very clear definitions and standards enforced in North America. For North America, there are 3 levels in general being defined. Level 1, which is the charging cable that you can plug into a wall plug at home or anywhere else, but that provides the lowest of charging capacity because of its limitation of that wall plug to 20 amps or so. Then we come to level 2, which is now more of a wall box or charging station, freestanding, like for commercial buildings, that provide, of course, more charging capacity. And then we come into inductive, which is, I would say it's more of in prototype, more of a testing phase, I would say for now. And then finally level 3, which is, of course, the holy grail of charging, which is provide fast DC charging using either ACE or CHAdeMO, or of course, there's also Tesla as well that is implementing their own standard for level 3. So that's the main 3 levels being used in North America, and each of them will introduce their own requirements for electrical safety as well. Of course, physically, they look very different. Level 3 will introduce a lot more infrastructure in general over that distribution. And level 2 will be a typical relatively small wall box or charging station. What is inside a level 2 charging station or level 3? Like I said, since we'll focus on that for today, for now, would be over voltage and over current protection. In the IEC world, this is an IEC picture. They call it an RCD, a residual current device type A. In North America, we call it more of a CCID that I'll talk about in a moment. A switching that will be either a contactor or a breaker. And then, of course, the control pilot communication between the charging station and the vehicle, the monitoring as well for ground fault detection. That will be what we find in private charging station. For a public one, it will be a bit more a user interface, communication for either 4G for an operator of multiple charging stations in order to in order to communicate the energy meter for billing, etc. But of course, the main electrical components remain the same. For a level 3, though, it's very different. Now we introduce a diode bridge, rectifier bridge, along with a power factor correction system, and finally, the DC-DC converter. So obviously now it's no longer AC, it's now they provide DC power into it. But overall, you may notice that there's also an RCD, so a CCID device at the input of the charging station. But of course, at the output of the DC output, there will be a DC ground fault relay. You may notice that will be the typical way of a bridge, like the one shown here in the picture. That's the one I mentioned that would have difficulty with switching power, switching frequency of converters inside of the EV. That's just a relative picture. It's not indicative of a bender technology. So for level 2, as I said before, they do not convert voltage. They only provide AC power directly from the building's distribution to the e-vehicle. And then inside the vehicle, there's an AC onboard charger to convert it to DC. There's a tri-national standard in North America that Canada, USA, and Mexico follow each other for a level 1 and level 2. And those standards, they refer to another one for the electrical safety for personal protection. For Canada, of course, we'll focus here on the C22.2, number 281.1. So that's the standard that is will be relevant for AC level 2 chargers, particularly for personal safety. The keywords being used in those standards are charging circuit interrupting device, CCID, and grounding monitor interrupter. I'll talk about that in a moment. But overall, that charging circuit interrupting device would be exactly what was highlighted in yellow, coming back to that picture. And there will be milliamps of the sensitive to the milliamps for ground fault sensors. The standard define 2 levels, CCID 5 and 20. So 5 milliamps or 20 milliamps. In terms of the the bender solution, that would be the product family, the RCMB series, that can come with different styles, of course, for very flexible designs for PCB or relay styles, different mounting configurations. And on top of that, the requirements for grounding monitor interrupter, that's another word for, let's say, we call it ground continuity, a ground check, that may be required if using CCID 20 milliamps. One of those relays would be, for that grounding monitor, would be the GM420 highlighted here on the bottom right. So speaking of the concept of CCID, what does it mean? So here, these are just snippets of those electrical standards I just referred a moment ago. They are defined as per the voltage and conditions of that charging station. So depending on the voltage, if it's a single phase or a typical 240 volts or 3-phase system, for example, there would be a different required features and that would be necessary inside that charging station. So when they say BI, it's in other words for basic insulation. Basic insulation between essentially the circuit parts and the accessible parts. So the insulation between the cables and the ground, essentially. So if you're using a basic insulation, then you'll be fine with a 5 milliamp, a 5 MIU. That's the term they use inside that standard for 5 milliamps detection. You could also keep using a basic insulation for cabling at 20 milliamps, but because it's a higher level of permissible ground fault current, there's an additional requirement of a grounding monitoring system. So monitoring, let's say, the ground cable between the charging station and the electric vehicle. There will be a need for a separate pilot wire to allow a ground check monitoring when you're using 20 milliamps. You could also, if you happen to use double insulation, then only 20 milliamps ground fault detection will be okay. Same thing for reinforced insulation. So speaking of the grounding cable I just referred to a moment ago, the connector here from the ground and the charging station, that is to provide equipotential bonding with across this charging station process. This is a typical configuration where the building distribution will be in all cases, I would say, grounded. Then the branch circuit will be then connected to the input of the AC charging station if it's charging cable, connected to the inlet of the vehicle that will go into the AC onboard charger and then conversion to DC. The typical CCID in North America, they are very similar to what we call RCD type A in Europe. They are generally rated for AC only ground fault detection around the 50 or 60 hertz in North America. So in the case of an AC ground fault, let's say one cable is connected to, or one of those inside that cable, the protection around that cable is stripped away, and one of the conductors is now loose, and it touched the ground, for example. Then a ground fault happens, and that's what is highlighted in red. That ground fault current will go through that ground conductor all the way back to the source of the transformer and back here through this zero sequence transformer. So a zero sequence transformer will see that difference between the inlet and outlet of that current through that same CT, and then it will return that as a ground fault, whatever is being leaking to that ground. So that also highlights another thing that is occurring nowadays, recently inside EV, is the introduction of power factor correction, PFC, inside the AC onboard charger. That introduces, essentially, that is being used for reducing EMI and power and raising power quality overall. But that introduces DC because they're using diodes conversion already before that DC conversion. So in Europe, they have identified this as a potential source of failure. Just like anything else, a diode can fail as well, and then that would create a DC fault current. In Europe, they have a requirement, and that's what you may have seen in the previous slides, a DC set point at 6 milliamps, and that's an IEC only requirement. It is not found in North America, and that's why it's needed on top of the RCD type A or GFI type A, I would say, and it's now commonly known as the RCD type B. As in that is able to detect AC and DC ground fault. And the reason is simple. And in case of a DC ground fault, it would take the same path along that is highlighted here with the red arrows, but through that CT, they will be, because of that BH curve, between the secondary and primary of a current transformer, that saturation curve, there will be a risk, essentially, of that DC current to alter the trip behavior because it will introduce an offset inside on that BH curve, essentially. So there will be it's commonly known as as DC blinding, essentially. This concept of DC ground fault on an AC only sensitive ground fault detection. Because of that, Bender, what we've come up with as a solution is all those products are AC and DC sensitive product. And we believe that eventually North America should introduce that as just the same as Europe, for the obvious reasons of raising electrical safety overall. So all those products are here, just a few examples of different mounting configuration, DIN rail, or the CT being separate that can be mounted elsewhere for passing through the conductors through the CT, or it could be like the RCMB 121, where the CT electronics are combined into one. Of course, if you mount it on the PCB, you would have to drill a hole to allow the conductors to pass through that CT, but that's where we also have a solution with the RCMB 131, where it's pre-wired. That's where it's shown here, that it's already pre-wired, so you don't have to drill a hole through the PCB in order to make those connections. All those products from Bender, they only provide the detection. So the sensing and the detection with the electronics, they do not provide the interruption, but they provide they always provide the output, the means in order to connect it to let's say the auxiliary of the contactor or the shunt strip of a breaker, for example, in order to make that interruption happen. So again, different options for different wall box designs. Just to highlight one example that in terms of flexibility, that would be the RCMB 121 series, because there are 4 variants available. I mentioned that if you, let's say you're looking for a charging station for North America only, CCID 5 or 20, then we have a model for that, for level 2 charging station. But for the IEC world, if you're looking for a charging station, you want to build a charging station for Europe, for example, then there are different requirements actually implemented there. For mode 2 charging cables, so the level 1 in North America, that will be the first one that has a need for 30 milliamps and AC and 6 milliamps DC ground fault detection. And if you're doing a mode 3 charging station or wall box, that will be a level 2 in North America. That will be an RDC 121, the 4th one. That will only be 6 milliamps DC. And if you're looking for both, let's say an hybrid that can be both be used for North America and Europe, then we also have a model available. So all this just to highlight the flexibility level that you can choose, and depending on what market even you want to introduce the charging stations. Now coming into level 3, and that I think that would bring me up to the end of this presentation. So level 3 chargers, the main difference is that they actually convert the AC to DC and then provide that power directly to the battery. So there's no AC, of course, it would not be connected to the AC onboard charger inside the vehicle. The standards for level 3 are different. Here they are referred, the 107 for Canada, UL 2202 for UL. But those standards also, again, refer to the same standards for personal protection, the 281 for Canada and UL 2231 for USA. The keyword being used in those instances is called isolation monitor interrupter, IMI for short. So that's why we're using this terminology in our documentation in general. So an example for level 3 charging and what will be the ground fault safety to be implemented here. The same idea starts again from the grounded system inside the building. There will be again the building always using grounded system. Branch circuit then goes into the input of the charging DC charging station. And that input there is generally also an RCD, GFI type A, only just before the isolation transformer. Then there's a diode rectifier to DC, and then that's where we found the IMI, the insulation monitor, and then up to the charging cable, to the DC plus minus ports of the vehicle connector with the DC contactor, and then straight into charging the battery. So in those cases, it falls into the responsibility of the charging station to ensure the high level of electrical safety for the wall's charging process. That would, however, create a problem where there would be 2 potential IMI on the same system. So when I mentioned the internal coupling switches, it could be internal or external depending on which IMI you are using. But the idea is that they cannot be 2 IMI, however, on the same system in this process. Because the 2 IMI, the 2 monitors, will see each other as potential ground fault, and in fact, their own measuring signal will interfere with one another. So that's why it has been regarded that the responsibility will fall into the charging station, though the coupling switches will isolate that IMI from the rest of the system, and this now has to take over everything from the source all the way to the batteries. So the same idea, the same importance of electrical safety that we realize that is important inside the EV now files, the same importance now files for that IMI as well inside that charging station. So again, the same capabilities of the reliable, precise measuring principle technology being used. So in terms of the product family that we are providing at Bender, here in this case, because there are it's fast DC charging, that would introduce higher level of leakage capacitance potentially. So that's why they are capable of those products are capable of a limit, of higher limit, up to 5 or 20 microfarad of leakage capacitance. They always have their own self-test functions to ensure that they are working as intended. They are ACE and CHAdeMO version, because CHAdeMO introduces different requirements for the measuring principle, and it can be used at up to 1,000 volts with an adjustable threshold and with different PCB and relay style availables. So in particular, the ISO EV425 is a DIN rail with a display up to 1,000 volts with up to 5 or 20 microfarad of leakage capacitance compatibility. We also have the I155 that would be up to, that is more of a PCB style for compact fast DC charging station. And then finally, we have the ISO CHAdeMO, ISO CH8425, that has a particular measuring profile and requirements for, especially for symmetrical fault detection. So these are the few examples here. These are main products available for fast DC chargers and ensuring the same level of safety that I talked about for inside the EV. So in conclusion, electrical safety, it's very important. It's of key importance for the mass integration of or mass use of EV in today's environment, for both the charging infrastructure, but also for the inside electric vehicle. You know, because protecting people from a hazard caused by the electrical current is, of course, should be a top priority, and that's why choosing the highest quality is also of key importance. So many of those aspects I've mentioned before about continuous monitoring during charging or while the EV is running in a very harsh environmental conditions, such as the variations of voltage, temperature, and switching frequency. That what really stands out when we look at the Bender product portfolio. Having multiple trip outputs and self-check capabilities is also another one. So whenever it happens even with a Bender or whatever, over time, 20 years later, for example, you will know about it because it has its own self-check capabilities. And finally, for AC and the DC blinding issue that I mentioned, that's why we have decided to incorporate the capability of detecting true RMS AC/DC measurements all the way down to the milliamps range. In fact, one of my colleagues, Torsten, had made a very good white paper about that topic of CCID in EV charging and the DC blinding issue. So if you'd like to know more, of course, we can share that with you. So that brings me, I think, down to the end. So thank you very much. Yeah, I think we're pretty much good to go for questions. If there's any more question, of course, we'll be happy to help. But more information can be found on our website, Canada, USA, wherever you are located. We'll be more than happy to help you. So thank you very much.
Thank you very much, Fred, for this interesting presentation. And now we're going to open the session for questions. So feel free to unmute yourself, ask the question, or post your question in the chat area. So Fred, we have a question from Kanija. It's what's the difference between grounded systems and isolated systems as described in UL 2020-31?
Yes. For the difference between grounded and ungrounded system, it's really referring to the grounding configuration of the isolating transformer. For example, in a building, the power source will be coming from a step-down transformer, and in a case, for example, a Y transformer, the neutral point will be connected to ground directly or with a resistor. That will be considered a grounded system. For ungrounded or floating system, it's in this case, this is a good example here. That isolation transformer is, as you can see, there's no connection between any of the winding of the transformer and the ground. So that will be generally regarded as an ungrounded system for that DC charging station. Because of that, the technology being used to detect ground fault will be very different. Compared if you look at the product being developed for level 3, it's an IMI that is insulation monitoring. But for level 2, we're talking about CCID with the zero sequence CT to detect ground fault. I hope that answers your question.
Hello?
Yes.
I'm George. Thank you for the presentation. My quick question. If your system is based on a signal that you inject into the DC rails, does that not propagate backwards through the transformer into the network, into the power supply network?
So it cannot. Overall, the signal has to, in terms of the IMI, it has to do a loop in order to detect that signal back. So that signal in this particular case will all, there will not be because there's a galvanic separation between the primary and secondary of the transformer. That signal cannot pass through. So it's really like, overcurrent protection, it's really limited to one network compared to the other. Putting a fuse in this system will not detect an overcurrent on the other side of that transformer. So the basic, that idea applies as well for an insulation monitoring, principle. With an injecting current signal, it will not circulate through that transformer. It will not also, in the case inside that EV, it will not pass through the other side of that galvanic separation of that DC-DC converter. So as long as there's a galvanic separation, that signal will not pass through the other side.
But the waveform you show us in one of the slides was rectangular on both sides of the zero value. So it's an AC, right? It's a
pulse DC, yes. It's not an AC as in, let's say, it's a sinusoidal signal. You are correct that it's between the positive and the negative of a signal, but it's still a voltage a current being sent through that signal, through that superimposed on that signal. And again, it's not like that signal would not pass through the other side of that transformer.
Okay, thank you.
You're welcome.
We have another question. What is the main reason for the capacitance limitation of your insulation measurement devices?
So it's coming back again to this principle of the signal, the pulse DC signal. A capacitance will be, in parallel to this RF, let's say, insulation resistance. So a pulse signal like this one will have, let's say, an effect where it will reduce, not reduce, but it will increase the time, the toll rate, R times C. That will be the toll rate of alternating current like this one. So that's there's also a limitation in terms of the filters, of course, being used. in being used in order to remove the noise of the insulation monitoring device. Those two aspects are what are limiting, in our particular case, up to a certain level. It has to be, let's say, 1 microfarad or 10 microfarad. Of course, it's a limit that we say in terms of our own requirements when it comes to measuring times, because the bigger the leaker capacitance, the bigger the capacitance itself. Like I said, the rate of R times C, the bigger the capacitance, the bigger that signal will take, to reach that full to make the full cycle essentially. So that increases the bigger leakage capacitance, introduce a lot more of a measuring time. And I didn't mention up till now, but there's a lot of going on behind the lines. We are not only taking one cycle of measurement. We're actually taking many of them to do an average calculation afterwards, and then take that value and output it as what is the measurement being done. So there's a lot of behind the scenes going on with the bender technology in order to reduce false trips and to make sure that it's not being interfered by noise or voltage drops.
Great, thank you, Fred. Is there any other question from the attendees? Okay, perfect. I just want to let you know, guys, for those who did not join us from the beginning of the webinar, a recording of the session will be provided to the attendees. And if you have any further questions, feel free to send it to me or directly to Fred. And we will do our best to get back to you as soon as possible. All right, and I believe since that we don't have any further questions, this concludes our webinar. Thank you so much, Fred, for your presentation.
Absolutely. Again, thank you, everyone. I just want to mention again, thank you, everyone, for attending. I really appreciate in those hard, trying times for your time to listen, to learn, and we're more than happy to help. If there are more questions, like you mentioned, if there are more questions being asked that would like more further clarification, we can continue that by email. So again, thank you as well, Mustafa, very much. It's for the opportunity. Thank you very much.
Thank you so much.